Okay, so I'm going to start 11.2, but yeah, so I flipped back. This is out of 11.1. This is on page 606 to the definition of analytic. So this definition is not too much use, but I'll state it anyway. Well, it's not too much use to us. If the Taylor series of a function converges to that function for all x in some open interval containing a, we say the function is analytic at x equals a. As far as we're concerned, analytic is just one of these words that mathematicians use when they mean like a nice function. Most functions that we deal with are analytic. For example, polynomial functions are analytic everywhere. A rational function, which a rational function just means a polynomial divided by another polynomial. Those are analytic as long as you're not dividing by zero. At a point where you would be dividing by zero, it's non-analytic. Yeah, and I think that's as much as we care as far as this video is going to go about analytic functions, because all the ones we're going to be dealing with are rational. Right. So we're going to talk about differential equations that look like this, or, I mean, if you have one that looks like this and you divide by a of x, you get, say, this, where p is like b divided by a, and q is c divided by a, right? Oops, I have to move this down. So a point is called an ordinary point if both the p of x and q of x are analytic at that value of x. We call that an ordinary point. Otherwise, we call it a singular point. So, what are we getting at? Is when does there exist a reasonable power series solution to such a differential equation? It's if a is an ordinary point, then we have two linearly independent solutions, each of this form. And notice this is a power series centered at x equals a. In almost all the examples we're going to be doing, a is 0. And that's been the case for all the examples we've done so far, and for the example we're about to do. But in general, you can talk about, of course, power series centered at whatever value you want. Oh, right. So the important part of this theorem is that it says something about the radius of convergence of the series that you can come up with. So the radius of convergence is at least the distance from A, so the center of your series, to the nearest, and this is important, real or complex singular point. So, right. Let's see. I guess I can jump straight into the example then. So we're going to find the general solution as a power series solution to this differential equation. And we're going to state the guaranteed rate of convergence and like what the recurrence relation for the coefficients is. So maybe let me do this guaranteed radius of convergence first. To do that, I want to get it in. So I want to get it in this form. So I want to divide by. This stuff on the y double prime. And then, right, so 0 is an ordinary point. Right, because these are rational functions. There's no problem if I plug in 0. I'm not dividing by 0. So that would be an ordinary point. The radius of convergence is at least the distance to the nearest real or complex singular point. So a singular point for a rational function, that just means dividing by 0. And this is real or complex, so I get root 2I. So the radius is at least the distance from the center of our series, which is 0, to the nearest singular point. And when we say distance, this is like in the complex plane, like 0's here. Like, yeah, hopefully you've seen these pictures before. But you have the real axis and the imaginary axis. Root 2I would be here. Minus root 2I would be here. We're looking from the distance between 0 and the nearest one. Of course, they're the same distance. So the distance is, I mean, it's just straight up and down. So it's easy to tell the distance is square root of 2. So the radius of convergence is at least square root of 2. Okay. So we got that part. Now for the rest, I just have to do kind of this messy manipulation of series. So let y be this power series. Y prime is this one. Y double prime is this one. Whoops. So this should have been n equals 1. This one should be n equals 2. Yeah, sorry. I'm just realizing that is too close to the edge. Yeah, we put this here. Yeah, sorry. I'm not gonna do it here because I don't like division. I would like it here. So yeah, let me get a new sheet of paper. All right, so I've got x squared plus 2 y double prime plus 4x y prime plus 2y equals 0. Okay, So we've done stuff like this before. This is just a bit worse. I would like to multiply this inside. Right, but yeah, so let me do this piece by piece. If I multiply x squared in here, I'm going to get cn and n minus 1 x to the n. If I multiply the 2, I'm going to get 2cn and n minus 1 x to the n minus 2. I'm going to multiply the 4x in here. So I'll put the 4 there. X to the n, right, because there's an extra x now. Plus, and then I'll just put this 2 inside. Okay, now where am I now? I would like to combine the powers of x. And I see x to the n here. I see a different power of x here. X to the n here, x to the n here. So I would like them to all be x to the n. So I'm going to re-index this sum. This is when I say I'm bumping n. I would like to bump this value of n up by 2. So instead of n minus 2, now this just says n. So how does this go? Okay, so unfortunately, I have to rewrite this thing, even though nothing is happening here. And then this is the one that I'm changing. So these values go down by 2. All the n's in here go up by 2. So this n is an n plus 2, this n minus 1 is an n plus 1, and n minus 2 is n. And then, oops, I won't change these. So I have to be careful to try to write them in the amount of space that I have. Okay. So let me carefully check that I did all these indices right. This one was a y double prime, so it should start at n equals 2. This one was a y prime, so it should start at n equals 1. This was y, so it should start at n equals 0. And then I multiplied this out, so these is n equals 2, and then this is from here, this is from here. Okay, and then this is the same. This one got bumped, so that's why this is now like this. Okay, so I think I'm good. So I'm happy that all the powers of x are the same. I'm a little sad that these indices, like these series, aren't starting at the same value of n. But we can deal with that. Some of these series, or 2 of them, have an n equals 0 term. So let me cover that. So when n equals 0 here, I'm going to get 2c2 times 2 times 1. So 4c2, and that would be x to the 0, so I just won't write it. So that would have an n equals 0 term. This one also has an n equals 0 term. Okay. there are also some n equals 1 terms. Like this one doesn't have an n equals 1 term, but this one does, and this one does. So let me cover that. So when n equals 1 here, I would get 2 times 3 times 2, so 12 C3 x to the 1. When n equals 1 here, I would get 4C1 x. And when n equals 1 here, I would get 2C1x. So actually, maybe I'll just change this 4 to a 6. Right, so once again, I got 4C1x plus 2C1x. So that's where that came from. Okay, now what's left, I took care of all of the n equals 0 and n equals 1 terms. So now the rest of the terms are all n starting at 2, and I can put them all together. I can combine all 4 series. So they all have x to the n, so I'm going to go ahead and factor out x to the n. What do we have other than that? I've got a... so what's the smart thing to do here? Yeah, so this is a terrible mess, of course, but so I'm factoring out the x to the n. I multiplied the n times the n minus 1 because, well, you're going to see what happens. Let me go 2cn plus 2, and then I'll multiply this out as well, n squared plus 3n plus 2. Plus this, so 4c1n, or cnn, right, plus 2cn, x to the n, and that equals 0. So this is, 4c2 plus 2c0 plus 12c3 plus 6c1 x plus right. So I have all these c sub n's. So I have c sub n times n squared minus n plus 4n plus 2. So I've got n squared minus n plus 4n plus 2. So that's n squared plus 3n plus 2. There we go. So, yeah. So this was a terrible mess of manipulating series, but I think we're done with the extremely ugly part. Now we equate coefficients. So this 0 on the right-hand side, that is the power series for 0. So all the coefficients are 0. So all of these coefficients should also be 0. So this constant coefficient should be 0. So for example, C naught would be negative, or yeah, sorry, C2, because I should solve for the larger subscript in terms of the smaller subscript. So if this is 0, C2 should be negative 1/2 C0. If this is 0, and I solve this for C3, it would be negative 1/2 C1. If this is 0, let me actually write this. This is 0, and it's kind of a miracle that in this terrible mess of algebra we got the same factor here and here. So I can just divide by that. And then I'm solving for C sub n plus 2. Negative 1/2 C sub n. In fact, that was true the whole way through, like this. And this is what we call the recurrence relation. Like in the instructions for this problem, it says state the recurrence relation. Right. So we're almost there. We almost have our final answer here. Let me now just try to state the general form of the solution to the differential equation. So right, let me show a pattern here. We found C2 in terms of C naught, we found C3 in terms of C1. This is going to be like an example we did last time where like the evens and odds have their own pattern. So C4 would be like, the way we do this is C sub n plus 2 is negative 1/2 C sub n. So C4 would be negative 1/2 times C2. Of course, C2 is just negative 1/2 times C naught. C6 would be negative 1/2 of C4. So that's just negative 1/2 cubed. So in general, C sub, say, 2m is negative 1/2 to the m, C naught. Similarly, I can start cranking out, say, C5. C5 would be negative 1/2 of this. C7 would be negative 1/2 of that. In general, C2m plus 1 is negative 1/2 to the m, C1. So y is we said y was this, but now I'm going to break it up according to the evens and the odds. So here's the even powers of x. I'll put x to the 2m. And the coefficient of x to the 2m should be c sub 2m, which was this. Now, I'll do the odd powers of x, so the power will be 2m plus 1, and the coefficient should be this. And this should cover all the odd powers. The first odd power would be x to the 1, so this should start at m equals 0, because when m equals 0, this gives me x to the 1. So that's the power series solution. Again, we can sort of see two linearly independent solutions. Like, this is a second order differential equation, so we really should have like a constant times this one plus a constant times this one, and the two constants are just C0 and C1. In fact, maybe it would look nicer if I pulled C0 out and C1 out, but I'm tired, so yeah, so then I will probably just give you a couple of problems out of 11.2 that are sort of like that. But obviously each one is significantly painful, so I'm not going to give you too many. Anyway, I'll call that video.